Welcome to the Creative Commons RX podcast. Before diving into this episode, I want to ensure we're all on the same page. This is for general informational purposes only and does not constitute the practice of medicine, nursing, or other professional healthcare services, including the giving of medical advice. No doctor-patient or pharmacist-patient relationship is formed. Using this information and the materials linked to this podcast is at the user's risk. The content on this podcast is not intended to substitute for professional medical advice, diagnosis, or treatment. Users should not disregard or delay in obtaining medical advice from any medical condition they have, and they should seek the assistance of their healthcare professionals for any such conditions. Clinical experts created the references, content, and clinical insight. NotebookLM, a Google AI tool, created the audio content, which I extensively reviewed before release. Finally, the host states that he takes all conflicts of interest seriously. Currently, there are no conflicts to disclose. For all of his disclosures and the companies he invests in or advises, he directs users to reach out independently, where he keeps an up-to-date and active list of all disclosures.
Let's talk about biologics. These things are some of the most powerful medicines we've ever invented, right? They're tackling cancer, autoimmune diseases, you name it. But here's the thing, these modern marvels have a huge secret. They are incredibly, fundamentally fragile, and keeping them safe is one of the highest stakes games in all of science. To really get why, you have to appreciate the mind-boggling scale we're dealing with here. Okay, so think about an aspirin molecule. Super simple, just 21 atoms. Now compare that to a biologic. We're talking about a therapeutic protein that can have over 1,300 amino acids. It's not just bigger, it's a completely different universe. It's like comparing a single brick to an entire cathedral. It's a piece of molecular machinery, a folded-up masterpiece. And that, right there, is the core of our story today. These drugs are absolute miracles, but they exist in this state of what scientists call marginal stability. That means their whole journey, from the moment they're created to the moment they reach a patient, is unbelievably perilous. So to really wrap our heads around this, let's use an analogy. I want you to stop thinking of a biologic as a pill. Instead, picture a priceless, impossibly intricate glass sculpture. Its shape is everything. If that shape breaks, even a little bit, it's not just damaged, it's completely useless. Game over. So why is this sculpture so delicate? Well, a protein's 3D shape isn't held together with superglue. It's held together by thousands of incredibly weak bonds. A tiny change in temperature, a little shift in pH, even just shaking it around too much, and those bonds can snap. And here's the kicker, the damage is often irreversible. So what are these forces that are always trying to shatter our glass sculpture? Well, there are a few main pathways to failure, and the scientists, the guardians, have to protect against every single one of them. First up is public enemy number one, aggregation. This is basically what it sounds like. The individual sculptures start clumping together. You heat them up, check them, or even just put too many in one place, and these sticky parts of the molecule get exposed. Then they just start glomming onto each other, forming this useless and potentially really dangerous gunk. Next on the list is denaturation. This is the unfolding threat. So if aggregation is the sculptures clumping together, denaturation is the sculpture itself just melting. It loses its intricate shape and becomes a useless blob. And get this, it's not just heat. Surprisingly, getting too cold can do this too. Once that specific 3D shape is gone, so is its ability to work. Period. And then we've got oxidation. The easiest way to think about this is like molecular rust, or maybe a chemical burn. If the drug is exposed to light or even tiny, tiny metal contaminants, it can trigger this chemical attack that damages key parts of the protein. It messes up the structure and just wrecks its ability to do its job. Now, here is the absolutely crucial part. These threats don't happen in a neat little line. No, they create a chain reaction. A little bit of unfolding exposes those sticky patches, which then leads to clumping. That new, messed up shape might then make it way easier for oxidation to attack. It's a domino effect. One problem just cascades into the next. So, how in the world do you protect these fragile giants? Well, you can't just cross your fingers and hope for the best. The scientists, the guardians, have a master plan. It's called quality by design. And this was a total philosophical shift. The old way was reactive. You'd make a massive batch of the drug and then test it at the very end to see if it turned out okay. Quality by design, or QBD, is proactive. It's about knowing the entire process so deeply that you're not just testing for quality, you are building quality in from the very first step. The absolute heart of this whole approach is identifying what are called critical quality attributes, or CQAs. Honestly, the best way to think of these is as the drug's vital signs. They're the specific measurements like how much clumping is there, is the shape still perfect, that tell you if your drug is healthy and ready for a patient. And there's a really clear, systematic way they do this. First, you define what a perfect drug even looks like. Then, you brainstorm every single thing that could possibly go wrong. And finally, use a risk assessment to zero in on that handful of attributes that are truly, absolutely critical for keeping a patient safe. But look, this isn't just some abstract science experiment. Controlling these vital signs has profound, real-world consequences for the person at the very end of this long chain, the patient. Because in the world of biologics, the stakes are just unbelievably high. Even the tiniest, seemingly insignificant change in one of those vital signs, one of those CQAs, can have massive, massive effects. Let's go back to aggregation for a second. Why is it such a high-risk CQA? Well, our immune system is designed to attack foreign invaders, and big clumps of protein look a whole lot like a virus. They can trigger a dangerous immune response that not only neutralizes the drug, but in the worst-case scenario, can actually cause the body to attack its own natural proteins. That's what happened in the tragic Eprex case. But here's what is so fascinating. Not all variation is bad. Check out glycosylation. This is the pattern of sugars attached to the protein, and it's a CQA that acts like a performance tuner. Scientists can actually engineer these sugar patterns to make a cancer drug a more potent killer, or they can tweak them to help a drug last longer in the body so a patient needs fewer doses. And it's the same idea with charge variants. Tiny little changes to the protein's surface charge can act like a switch. They can affect how well the drug binds to its target or how long it can survive in your bloodstream. If you understand the CQA, you can literally control the drug's potency and stability. It's incredible. But the Guardian's job is not done when the drug leaves the factory. Not even close. The final journey, what they call the last mile, to the clinic, is often the most dangerous part of all. So, you've done it. You've made a perfect product. It's sitting there, safe in a vial. The journey must be over, right? Nope, not even close. In fact, some of the riskiest handoffs are still to come. Think about what happens in the hospital pharmacy. When you dilute the drug to put it in an IV bag, you also dilute all the special ingredients that were protecting it. If you use the wrong fluid, say dextrose when it was designed for saline, the drug can clump up instantly. The medicine can literally stick to the inside of the IV bag, which means the patient never even gets the full dose. And all of this depends on an absolutely unbroken cold chain, keeping that drug between 2 and 8 degrees Celsius every single step of the way. So this entire philosophy, this whole complex world, really boils down to a simple, powerful 3-part strategy. 1, identify what is critical for the patient. 2, learn how to control it across the entire life cycle, from the factory all the way to that IV bag. And 3, prove with hard data that your control strategy works every single time. That is the scientific argument that gets a drug approved. And that leaves us with one last big thought to chew on. In the world of biologics, there's a famous saying, the process is the product. If that's true, if the journey itself is what defines the medicine, then mastering this incredible, beautiful fragility is the absolute key to unlocking the next generation of these life-saving cures.
This is for general informational purposes only and does not constitute the practice of medicine, nursing, or other professional healthcare services, including the giving of medical advice. No doctor-patient or pharmacist-patient relationship is formed. Using this information and the materials linked to this podcast is at the user's risk. The content on this podcast is not intended to substitute for professional medical advice, diagnosis, or treatment. Users should not disregard or delay in obtaining medical advice from any medical condition they have, and they should seek the assistance of their healthcare professionals for any such conditions. Clinical experts created the references, content, and clinical insight. NotebookLM, a Google AI tool, created the audio content, which I extensively reviewed before release. Finally, the host states that he takes all conflicts of interest seriously. Currently, there are no conflicts to disclose. For all of his disclosures and the companies he invests in or advises, he directs users to reach out independently, where he keeps an up-to-date and active list of all disclosures.